802.11 physical layer technology. So this is the objective. Upon completion of this class, you'll be able to describe concept of 802.11 physical layer, including the spectrum technology, the direct sequence spectrum, and also including the orthogonal frequency division multiplex. So the content number 1, the physical layer description. So this is the working group for WLAN. So we have the physical and also the MAC. So on the physical layer, right here we can see many different versions of the wireless. So we have 802.11, B, G, AN, and also the AC. When we're using the LAN connection, so we will base on our physical device, like the hardware that we're currently using. So we check on the port, the physical port. So which port they can support 1 gig or maybe 10 gig, 40 gig or 100 gig. But to the Wi-Fi, they're using the standard discount version to differentiate currently the wireless in watt speed. So then for the MAC layer, so they have a 802.11e. So this standard will be used for the QoS. 11H is that using for the TBCA, DFS. I is mainly for the security. R is for roaming and S for the mass. This is the overview for physical layer. So they have following technology in WLAN. The first one is the IR, infrared. Then we also have the wireless radio. Radio frequency mainly use spectrum technology, which included the FHSS, frequency hopping spectrum, okay, or DSSS. Okay, so this one will be the frame format for the physical layer. Okay, on the top they will have the WLAN MAC, and then PLCP. Follow-up is a PMD, and finally they're going to the standard choosing. So they know currently for the wireless, so they're using what kind of the version, okay, BG, AN or AC. Then for the bandwidth, so bandwidth is depend on the volume of the data to be transmitted. So for those of the voice, the FM signal, they only carry the very less information. So that's why the channel, they only carry this frequency. Okay, this only have a very small usage. When we go for the TV signal, so the TV signal have 4,500 K. Okay, this is the kilohertz. Okay, this is hertz. And for our data signal, so signal is occupied 20 megahertz. Okay, this is 20 megahertz, and this is further proof the reason why in our some of the scanning software, you notice when we're using one of the channel, like example, this is channel number 1. Okay, and they further prove why our channel is so wide like this. Okay, so this is the range we have 20 megahertz. Okay, 20 megahertz. Okay, so this is the size because we currently using this one is for the signal. Okay, then the next one, the spectrum, effectively prevent the interference. When we're not using the spectrum, what will happen? So like example, right now, we are in the same channel. So this is the channel number 1 that we're currently using for our SSID. Okay, channel number 1. So this blue color highlight places is a user signal. We're inside the channel number 1. At the meantime, they also have some other interference located in the channel number 1. So this is the interference. So we'll get the full interference from this channel. So it will cause our signal become very weak and unstable. So this is the reason why we have to using the spectrum. With using a spectrum, our user signal will become like this. So this is the reason why you can see our channel occupied like this one, channel number 1. Then we have 20 megahertz. So actually become like this already. So right now the interference signal is only at this channel, okay, at these places. But for other area, it's still perfectly fine. It's no problem at all. So they're using this kind of technology can able to prevent the interference come from the same channel. So this is the frequency band. Okay, yesterday I did also do some explanation about the ISM. Okay, the ISM stands for the industry, science, and also the medicine. Okay, so all the band here, they have their own range. So right now for the wireless, we're actually using the band in the S band and also the M band. So the industrial band is mainly for those of the FM, the radio broadcasting channel. Then the second, physical layer technologies. So there's 3 physical layer technology. The first one will be the FHSS. Then follow we have the DSSS, and the last one is OFDM. So let me start from the FHSS. So it's a matter of transmitting the radio signal by rapidly switching the carrier among many frequency channels. It's using the pseudo-random sequence known to both transmitter and the receiver. So this is happening to the very, very first the wireless technology. Okay, when it is not yet very mature. So this is happening to this version 802.11. Okay, without any version behind. So at that moment, how they actually prevent the radio interference? So they're using the FHSS. Okay, maybe I'm going to draw another graph. So like example. Okay, this is like, oh sorry, my light is so bad. Okay, like this. Okay, this is channel 1. So this is my current channel, and okay, we know channel number 1 we occupy around like 20 megahertz for this channel. Okay, so this one is my channel. So inside this FHSS, how they actually going can able to prevent the interference. So as what we know, in the channel 1 here, we still have many spacing. Okay, for doing the data transmission. So what they're going to do here is, okay, like example right now in the channel number 1, I have many the sub channel right here. So I'm only using this one to do the data transmission. Okay, this is the channel that I occupy. So at this moment, I'm using the channel right here, and okay, there's another interference places. Okay, this channel they have an interference. So okay, this is the interference source. But no worry, because right now I located in this channel, so I won't get any interference. Then the next second, I'm going to move my channel to another area. Okay, this is my next second. My channel changed to here. Then the third second, I will jump again. Then follow up, this keep jumping. So maybe one of the second you hit on the same channel as an interference source, but it's still fine because this is just like a few seconds, then you get the interference, but most of the time the network is still very stable. Okay, so this is the reason why they're using the FHSS to prevent the interference. So they call it as a frame hopping. Okay, right here you can see this one is the channel frequency slot, and every second you keep changing the channel for every seconds to prevent the interference. Then the next, the DSSS. So for this one, as I did mention earlier on, so they're using the spectrum to prevent the interference from a single channel. Okay, so I only have one places get interference. Okay, this is the places get the interference, but the rest of the places is still fine. So this is a continue for the DSSS. So now we already understanding the FHSS, how to prevent the interference. So they're using the frequency hopping to prevent the interference. But how about for DSSS? So the DSSS also know about this problem. So it's going to divide our bit into 11 chip bucket. Okay, like example, we have the information. Okay, the bit information 1010. So what's the meaning of the chip bucket here? So when we're going to transmit this information, this is binary. After we're doing the modulation, transmit to the A. So they become certain radio wave. Okay, so this radio wave, they carry the bit information. So based on what kind of modulation that you use. If you still remember, we have AM, PM, and also another is called FM modulation. Okay, it's 3 different types of the modulation. So every single modulation you're doing to modulate based on bit by bit. Okay, so if one of the bit here, they get interference by other source. So maybe the information become inaccurate anymore. Okay, so to prevent this kind of the problem, so they're going to correct this one become 11 chip packer. Like example here, 1 bit they become this 11 chip packer. 0 is this. So this is only 4 bit. Then they become a lot of information. Okay, then your radio wave will become very long. So why they want to do this one? Because if for this kind of chip packer, when they get any interference, like maybe I have some of the information lost. Okay, all the information lost, but still fine. As long as you have 2 bit, can be still recognized. So the transmitter and also the receiver can always recognize right now this chip packer is belong to 1, refer to the bit number 1. And same to here. Okay, this is my chip packer. When I'm doing the transmitting, then I notice some of my bit is already lost. Okay, this is the bit I remaining. When the receiver receives this chip packer, they know I'm going to identify 01 is the beginning and the 111 is the last. So I know, okay, so this is actually referred to the 0 bit. Okay, so this is the function of the chip packer to prevent the interference. Then the next one, we have the CCK, complementary code key. So this one also can effectively prevent the noise and the multipath interference. So the CCK actually is more complex if compared to just now the chip packer. Okay, so why they're using the CCK? Because they want to improve the transmission rate. Okay, so with using the CCK, the maximum transmission rate can reach up to 11 megabit per second. Okay, this is for the B. The disadvantage, to prevent the multipath interference, CCK use complex technical and is very difficult to implement. Like this one. Okay, so the modulation for the DSSS. So this is a very simple way to doing the modulation. They have the BPSK and also the QPSK. The BPSK doing the modulation is based on bit by bit. Like right now you have the information 1100. Okay, so this is the information you want to send to another receiver, okay, to the PC. Okay, go to the wireless. So when you're doing the modulation, bit number 1, okay, just an example, okay, for the BPSK. So I know when none carry any information, my radio wave will be look like this form. When carry 1 bit information, my radio wave will become this. Okay, 0 and 1. So when I'm going to convert this one become the radio wave, then it will become 1100. So like this. And then 00. Okay, let me change the color. So they become like this. So this is 1100, the radio wave. Okay, so this is based on bit by bit. And the other one is happening to the QPSK. So the QPSK is allow us to do the fast modulation and allow us to carry more information. So it's the better version compared to the BPSK, because the BPSK is based on bit and the QPSK is used 2 bit to do the modulation at the same time. So the previously I did mention when my bit is 1100. So every single bit here they have their own radio form, but the QPSK they have 4 different types, because when they're doing the modulation they're using every 2 bit. Okay, like example here, they have 00. Okay, this is 11. Okay, so they actually have some of the calculation, okay, to do the modulation. Like example, this one. This one they're actually doing the 2-bit modulation. So they have something is called the cost bit. So right here they have the cost, and also the sin. Okay, actually it could be very complex, but I just made it more simplified. So the cost. Okay, okay, for the let me write out most significant bit and also the least significant bit. So right now my information is 0 and the least also 0. So right now I'm doing the modulation for both also 0. Okay, so right here 0, this is for the cost. Okay, sorry, I'm using the mouse to write, so it will be very bad. Okay, so the cost symbol will be look like this, the radio wave, and the least significant bit is a sin. Okay, this is 0, so the radio wave will be look like this. So it will going to combine both together, and become another type of the radio waves. So maybe the radio wave is chain. Okay, become like this. So this is the other type of the modulation in the QPSK. Okay, then you know, okay, right now this one is belong to which degree. Okay, then this is the DSSS coding. If you're using the coding mode using the Barker way, okay, the Barker in the BPSK we can achieve 1 megabit per second. If the modulation is a QPSK, so the QPSK using the Barker coding method, we can get 2 megabit per second. And then we try to using the 4-bit CCK. The 4-bit CCK allow us to achieve 5.5 Mbps, and of course the 8-bit can achieve 11. Orthogonal frequency division multiplexing. So this is a multi-carrier modulation technology. So we know the previous one, the DSSS and also the FHSS, when they're doing the modulation, okay, in one channel. Okay, no matter using the FHSS or the DSSS, they're doing the modulation. They will fully utilize all the channel here and doing the modulation. But inside the OFDM, they're doing a different thing. So in one single channel, you're going to divide the multiple sub-channel. Okay, they have a lot of sub-channel inside here. So every single sub-channel we're doing is on job. We're going to do the modulation by itself. So they can able to do the modulation very fast in this way, OFDM. Okay, they divided one channel into multiple sub-channel. So this is what I mentioned just now. See, this is an example in the 5 GHz channel. From here, you can notice using the OFDM, they can divide the channel into 48 sub-channel for the data transmit. And another 4 sub-channel is purely used for the phase reference. Okay, they have 4 is reserved. Sub-channel modulation here. They can do the BPSK, like what I did explaining just now. They're doing the bit-by-bit modulation. And then the QPSK. So the QPSK can perform the modulation up to 2 bits at the same time. And then the last one, the QAM, okay, the quadrature amplitude modulation. Okay, QAM. So this one can able to do the modulation more than 2 bits. So maybe they can do the 4-bit modulation at the same time. So QAM use the carrier amplitude and the phase to transmit information. Combining with QAM modulation, the OFDM provided up to 54 Mbps. So they can be even more complex. Okay, the calculation inside the 16 QAM or the 64 QAM. Okay, so they're using this kind of the amplitude and the phase to get to know what is the radio waves belong to the current symbol. Okay, like example right now I have a 0010. So after they're doing those of the calculation, they know this dot right here, they actually refer to the symbol like, okay, first is short, Okay, will be like this one. 000 maybe it's just remaining the original form without changing the forming of the radio. Okay, this is even more complex, 64. And this is for the 256. And this calculation is very hard anymore. So we no longer can using the formula to calculate. Okay, so basically the system will do it for us. Okay, right here, let's look at the table. So we show the different type of the modulation methods, data rate and the actual rate. So right here we notice the BBSK. Okay, the BBSK, they're using half for the data rate, and another half is reserved for the data correction. So when I transmit the radio wave, and at the same time I receive some of the interference, so they'll cause some of the signal loss or error. So they always reserve half of the data rate is for the corrections. So the BBSK have half data rate, only can achieve 6 Mbps. If I'm going to change the data rate become 3/4, so I can able to get 9 Mbps. Okay, so this is the maximum for the BBSK. For the QBSK, the half we can get 12. 3/4 we can get 18. Then we have 16 QAM, 64, and also 256. So as you can see, the 256 can able to using the 5/6 for the data rate. So that means I only require very less rate is only for the data correction, or I focus on the data rate. So this is the reason why we can get 217 in 256 QAM. Okay, this is the comparison here between the different standard. So basically B and G using the same frequency band. The distance for all the channel is the same. Okay, every single channel, the distance is around like 5 MHz. For the modulation, B and G both support DSSS. And this is the reason why the G is compatible with the standard B. Okay, because they both have the same modulation. And the G can able to achieve 54 Mbps is because they're using this modulation, OFDM. To the A, 802.11a. This one is only can work in the frequency band 5 GHz. It only support OFDM modulation. So from here you notice, as long as the standard can support OFDM, both of them can support the speed up to 54 Mbps. For the 802.11n, so they can support both 2.4 and also the 5 GHz frequency band. So since both also using the OFDM, but why the 11n can achieve even faster than the A or the G? Because they have this MU-MIMO technology. Okay, not only like that, they still have many features, and I will going to cover it later on. Okay, and the last is the AC. Okay, this AC work in the frequency band 5 GHz. Okay, they also support MIMO and the OFDM, but this one can achieve up to 3.47 gigabit per second. So this is summary here. So I already discussed the physical layer concept, spectrum, DSSS, and the last one is the OFDM.